Hello and welcome to your week 7 video for NUC 110. For this week, I want you to review the test number 2 key, which we'll look at here in a second, then review the ECCS and the HIPSI PowerPoint and the video you're watching now. Define about 10 terms, and then tell me the automatic initiation signals for each of the ECCS systems. And then there are 2 videos here to watch. So you don't have to write anything about these papers. It's just showing you basically how a HIPSI pump works. So let's take a look at the test. So what's giving us the motive force for the jet pumps? And that's the recirc pumps. So remember, these are the drivers and these are the driven flow, right? Driving flow and driven flow. The reactor recirc pump gets its water from that outside of the reactor core, right? There's that plenum, just kind of like a little pool inside of a pool, right? The kiddie pool there is the core, and outside that is that plenum area. And then water from the jet pumps gets pulled in there as well as it goes on its way underneath the core to make up the total core flow. Water is our coolant. And then when you see the word inert, you should start to think about nitrogen. So all these other things are not going to be inert because they have oxygen in them, but nitrogen is inert. So the reason why we put nitrogen in the dry well is because nitrogen cannot catch on fire. So it's really good to put in there just to prevent fires. So control rods are going to absorb neutrons, and as they do that, they stop the chain reaction, they stop the fissions. So what happens when recirc pump speeds go up? That's going to cause reactor power to go up because we push the water up the fuel, so we get extra moderation, and that extra moderation leads to increased reactor power. A LOCA is a loss of coolant accident when we have water leaking out of the reactor. And a hydraulic control unit, an HCU, we put them up to about 1,000 pounds of pressure with, again, nitrogen. Air is going to be corrosive inside there, so we don't want to use air. We want to use nitrogen. There's a little fad with tires a couple years ago where they wanted you to put nitrogen in your tires instead of air, but it's a lot more expensive, and the corrosion on the inside of your tires is going to be relatively minor compared to the fact that you're driving on them. So in a PWR system, it's going to clean the reactor coolant, and it's also going to keep the water borated. So that's the second way that they control power in a pressurized water reactor. They can't just turn the recirc pumps up to push in more water because it's already water solid. So a check valve is going to allow water to go in one direction, and a relief valve is going to stop water from over pressurizing. So you can't get too much pressure because this relief will open and let the pressure out. So demineralizer is going to clean the reactor water and prevent corrosion. So CVCS, that's a PWR system, and it's different from reactor water cleanup because they add boron in. So boric acid in a PWR is just a control power. So a break in the suction line of a reactor recirc pump is going to cause a LOCA, and it could reduce the water to 2/3 of core height because, again, we have that pool inside of a pool. So as low as the water can get is 2/3 of core height, and then we'll turn on our ECCS systems that we're talking about this week to add that extra third in. So the main condenser is a heat exchanger. PWRs have 2 different types of control rods. They have shutdown rods and power control rods. So 2 things that we use as neutron absorbers are boron and silver. And if we have radiation measurements going up throughout the plant, we could have fuel damage. Control rod malfunctions is one people pick a lot, but if a control rod malfunctions, that would not cause radiation to go up throughout the plant necessarily. But if we have fuel damage, that means that the fuel is leaking out and it's going all over the plant. So fuel is normally located in dry cask storage, the fuel pool, and of course the reactor. Those are the only 3 places that we want fuel. If it's in any of these other places, that is a bad day. So fuel is enriched to increase the uranium-235 content. So uranium-238 is about 99.3% of what we get out of the ground, and about 0.7% is uranium-235. So for our American light water reactors, we like to run this percentage up to about 5% uranium-235 and about 95% uranium-238. So if we have failing tubes and a heat exchanger, again, we can get increased radiation throughout the plant because there's going to be some radiation in this coolant, and the radiation will start to basically propagate around the plant. So how does vacuum form in a condenser? I drew this one on the board, right? We have a set volume and it's sealed and it's full of steam. When that steam condenses and becomes water, it takes up a lot less space, a lot less volume. So when it does that, there's nothing left behind because it was a sealed state, right? So now we have a very low pressure region up at the top and just a little bit of water down at the bottom. How do the jet pumps work? We've got the Venturi effect. So the nozzle creates a very low pressure there at the tip, and that pulls all the water in from that surrounding area. And the water is forced through the nozzle by the recirculation pumps. So why do we have collet fingers? Those are on the control rods. Those are our little finger traps. So if I try to withdraw a control rod, it's going to say, no way. It doesn't want to be accidentally withdrawn. What I'm going to have to do if I want to withdraw it, I'm going to have to insert it a little bit, and then those collet fingers will let go, and then I can pull it out because we don't want to make a mistake and accidentally pull out the control rods, and we also don't want them to fall out if something goes wrong mechanically. So how do we use that annulus region? So we're talking about, we have the core, and then outside of the core is that extra little pool where the jet pumps are. And the basic idea is that if the recirc pump just falls off for whatever reason and water starts leaking out, only 2/3 a core height will still be covered, right? 1/3 can be uncovered, but that's why we have our ECCS systems. So the downcomers from all of our steam dryers and steam separators are there as well. So that basically some gutters are going to bring that water back into that area and keep it full. So I cheated here on my drawing a little bit. I just used the drawing out of the PowerPoint. So the main things that I'm looking for on this drawing are the valves that have numbers on them. So scram inlet, scram outlet, I want the words and things. So this valve and, some of these things, it's fine if you have them or not. You also need to make sure that you have the piston. So the next question, I believe, is how do you scram? So to scram, all I have to do is scram inlet and scram outlet. So the water is going to rush in, go underneath. The water on top needs somewhere to go. It's going to go out the scram outlet and to the scram discharge volume, which is just a tank where we can hold some extra water. And then the other one is how do we withdraw the control rod? So we need to get those collet fingers to come loose. So we're going to run water through the 123 and up and just bump it up just enough to get the collet fingers loose, right? And this water on the top is going to go up through 121 and exhaust. So now my collet fingers are loose. So now I'm going to close those two valves, the 123 and 121, and I'm going to open the other two. You can see they're solenoid valves. They're controlled by little electromagnets. So now I'm going to open 120 and 122. The water's going to come in and it's going to push the control rod down, right? The reactor's up here on the top. The water on the bottom needs somewhere to go. So it's going to come out and come through the 120. There we go. And out the exhaust. So being able to understand this drawing and understand how the rods are inserted and withdrawn and scrammed and things is very important, especially for anybody that's going to be working underneath the reactor vessel. So here are the definitions. Everybody did pretty well on these on the homework. And again, you can just look in the slides because you're doing a take-home test. So it's a little bit easier. And another drawing where I cheated. So it tells you up here in the description what I'm looking for, right? So include the reactor vessel and then the suction. So I'm asking where the water comes from, right? It's coming from here on the recirc pumps. So then where does it discharge? It's going back into the feed water line. So that's its path back into the reactor vessel. Then I'm asking you for heat exchangers. You need to know there's 3 regenerative heat exchangers and 2 non-regenerative heat exchangers. And then tell me about the pumps. We got 2 pumps here. We got 2 demineralizers. And then I want you to be able to draw all the different pieces and pipes. So it'll come off here, come down and around and through our heat exchangers. I'm looking for the path myself now. This drawing is complicated. I'll give you all that. So it's going to come down and through all of our heat exchangers, up through our pumps, back down through our demineralizers, and then make its way back into their reactor. If you're having trouble with these drawings, please come in and ask, and I can draw them on the board, and it'll be a little bit simpler than it is whenever you're looking at this crazy thing. Trying to simplify that on the test. PWRs have 2 different types of rods. I talked about that a second ago. And then this drawing was from the first test and everybody did well enough on it. We've got our reactor, turbine, condenser, the pump. This is the feed water pump in this case to push it back into the reactor. So there we're making our nice closed loop. The condenser is attached to some cooling body of water. And that is it for the test review. So let's take a look at ECCS. So this is one of the things they disabled at Chernobyl, which now if you try to disable this, the reactor is going to call you stupid and it's going to scram itself. It's not even going to let you turn it off. It's just going to scram itself before you can actually turn this ECCS system off. So here is our reactor vessel in orange. Around the reactor vessel, you'll see the dry well. And then here, this is a donut shape. So it's coming out towards us and going in over here and going around the back of the reactor. So this little donut is called the torus. And that's just a nice big volume of water, as well as a place for us to discharge extra pressure. So if my reactor in an emergency starts to have too much pressure, I can just open some valves and dump the water out underneath this water to relieve reactor pressure. So when they were designing this, they want if there's a leak, we need to find some way to add that water back. So, somebody dropped a steel girder and knocked a pipe right off the side of the reactor, right? That's the design basis accident. So they kind of were like, what's the worst thing that could happen to this reactor vessel? And they decided that, a steel girder coming and just straight up chopping off one of these lines. So they designed that annulus region so that we only go down to 2/3 of core height. And then we have core spray in here that does exactly what it says, spray the core. So keep that water a little bit higher than 2/3 of core height just to make sure the fuel stays covered. So there are two mechanisms. We need the containment to limit the radioactive release to the public. That's a huge part of it. So one core spray pump at full flow will cool an uncovered core. So even if the water were to totally go away, if I have one core spray pump, it's going to totally cool the core. So we have more redundancy besides just the two core spray pumps. We have this other system, RHR, residual heat removal. So that's another one. And we have a third one called HPSI, high pressure coolant injection, that we're going to talk about in the second half of this video. So inside the core shroud, we want to maintain that level above 2/3 of core height. So we can't drop a steel girder inside the reactor. There's no way to do it, right? It's going to plinko off something else. But if one came out outside in the dry well and knocked something off, we would still have water above 2/3 core height. So LIPSI is a different system here, and we need two of those pumps. So we built four. So if I lost core spray and the girder fell off and knocked my pipe off, well, now I have LIPSI, and I have four of those, and I need at least two of those to start recover and level. If I only have one, then I'm just going to maintain the level. Whatever, if I have 2/3 core height and I have one of my four LIPSI pumps running, that's just going to maintain level, and that is going to be good enough. So adequate core cooling. So how do we decide if the core is cool enough? So the best way to do that is to have the core submerged. If the water is on top of the fuel, we're going to be fine. And the magic number here is 2200 degrees Fahrenheit. As long as we can keep everything below 2200 degrees Fahrenheit, we cannot build up too much hydrogen, so we won't have an explosion. So Fukushima let their fuel get too hot, and once it goes above this number, you start to build up hydrogen. And if you decide to try to vent that hydrogen or get rid of it somehow, it is going to explode as soon as it sees oxygen. So if we can't submerge the core, we could start trying to do fancy stuff like steam cooling. So, I'm using the steam to remove the heat, and I'm at this low level 4, low level 5. These are the end times, right? Low level 1 and 2 are emergencies. Low level 4 and 5, we're getting down to like, panic time. We're using steam to cool it instead of water, which is very, very, very bad. So the loss of coolant accident, the hypothetical accident is that, water's going out faster than it's going in. So something broke somewhere and the water's going out faster than it's going in. We'll try to isolate the leak and figure out what's causing it. And once we do that, we'll make sure our core spray is filling up the water fast enough. So emergency core cooling system, its main purpose is to act in conjunction with the primary and secondary containment, which the primary is going to be the reactor vessel, the secondary is going to be the building, to limit the release. If we do have a design basis accident, right, a DBA, where something fell and knocked off a pipe. And CFR is the Code of Federal Regulations. So this is something that we have to do to stay in compliance with federal law. So somebody standing at the fence for whatever reason with their fingers through it and gawking, if they stood there for 2 hours, they wouldn't receive more than 25 rem, which that is a tremendous amount. We don't want anybody getting 25 rem, especially not in a small time like 2 hours. So you want to make sure they don't get more than 300 rem from iodine exposure. So if that iodine makes its way out of the reactor, we want to make sure that nobody gets that iodine exposure to their thyroid, because iodine sticks to the thyroid and causes a lot of harm. ECCS is also going to give us a heat sink. So say for whatever reason we've lost the river, we have that nice big torus and it's full of water, hundreds of thousands of gallons in there. And it's going to give us a chance to remove all that heat once the reactor is shut down. So Fukushima was able to shut down. They got the control rods in, but they boiled all their water off. So they needed this heat sink. And then eventually they had to vent the reactor. So we want protection from a primary line break. So if an earthquake came, we have seismic protections in there to make sure that that is not something that is going to cause a line to break off. So if a line, this is our defense in depth. So if a line does break off, then we're going to have two independent sources of cooling. So we can have a flood and a spray. And we want to make sure that immediate operator action is not required. So if we have a really big earthquake and all the operators fall over, or if for some reason the control room has to be evacuated, we have 10 minutes before an operator has to do anything. So the computer will take over. We would prefer to have the humans doing it because that puts them in more control. But if the humans cannot do it for whatever reason, the computer will take over for at least 10 minutes until the operators can get somewhere where they can take more action. So the law requires us to have the reliability. We need capacity, we need diversity, and reliability to redundantly cool the core. And we want to make sure that we have water inside primary containment, which is that torus. And we also have a backup to the torus called the condensate storage tank. So a tank that's sitting outside, just full of water again, ready for us to spray on the reactor as needed. These systems can be automatically initiated if it senses a condition that it doesn't like, which is one of your questions this week for the week 7 assignments. And you want to make sure that your systems are testable, because I don't want to just have them sit there and not do anything. Like the emergency brake on your car, you can't really test it. If you're driving down the road at 30 miles an hour and decide to test your emergency brake, that's going to destroy your emergency brake, basically. So we want to make sure that our core spray systems and our RHR systems and everything are testable so that we can make sure they work. And we'll usually test them every 1 month or every 3 months, depending on which system it is. So to protect from physical damage, when it says missile, it's not talking about, Al-Qaeda coming out and shooting at the power plant. It's more so talking about like a nitrogen bottle falling over and shooting through something. Fluid jet, so steam comes out of there at a really high pressure. We want to make sure that's not causing any physical damage. And we want to make sure our pipes, if when they come on, that they don't herky jerk too much. And then environmental qualifications, because it's going to be hot and different temperature things are going to be going on. So we want to make sure that we're using, a lot of concrete. We want watertight doors, keep fill systems to keep the pipes full all the time. And if the systems are full, the pipes won't whip as much. So this pipe whip happens a lot worse if you don't have keep fill, keeping the pipes full of water. So now let's talk about our 4 ECCS systems. So there is another PowerPoint in the future for each one of these. So, this is kind of a short explanation of what they are, but we will go into more depth and more detail as we go through each one of them in their own slides. So HPSI, high pressure coolant injection. So it's important to know which ones of these are high pressure and which ones are low pressure. So HPSI is going to give us makeup cooling to the core if there's a small break. So the reason why we say a small break is because the pressure is high. So you can imagine if the reactor got lopped in half, all that pressure is just going to rush out into the dry well. So now I'm not going to have a very high pressure in the reactor vessel. But if I have a very small break and the water is at 1,000 pounds in the reactor, it's going to push it out. Even if it's this, 1-inch break, then I'm going to need something to make it up. So I need my high pressure injection so it can overcome that 1,000 pounds of pressure in the reactor. So the trade-off for the high pressure is that you don't get nearly as much flow. So normally the water is going to come from that condensate storage tank, a 100,000 gallon tank that's sitting outside, but I want it to be redundant. So I have a backup, which is that torus or suppression pool. So something interesting about this one is that the actual pump is powered by steam. So that steam coming off the reactor, it was going to lower the pressure a little bit for us, and also it's going to spin this pump to make it pump the water in. And everything, all the valves are DC powered, which is batteries. So the only thing that's not DC powered is the pump, which is powered by steam. So if I have a total station blackout, my grid got wiped out by a hurricane and my diesel generators are not starting up, I still have this HIPSI system, but even if I don't have AC power, which AC is what we're getting out of the wall. So it can go, from this can operate up well above 1,000 pounds all the way down to 150 pounds. And the flow is going to go with the pressure. So a high pressure is going to be a much lower flow. If I get down to this lower pressure, I'm going to have this very high flow of around 4,000 gallons per minute. So HIPSI has a backup called the automatic depressurization system. And that system does what it says, right? Automatic depressurization system. It opens some valves and dumps the steam from the reactor straight into the suppression pool. So once that happens, the pressure goes down and my low pressure systems can kick in, right? Low pressure coolant injection and core spray can kick in to push that water onto the reactor vessel. So here's our automatic depressurization system. We've got 7 safety relief valves. And remember on the last test there, we talked about relief valves. Those are just going to open up when they see too much pressure and relieve the pressure and send it, in this case, straight to the torus. It backs up HIPSI, and it's going to basically go until the low pressure systems kick in. So that's going to open up and start blowing the steam off. And once the pressure gets low enough, my low pressure systems will kick in. Each one of them can put out quite a bit of steam, and I have 7 of them. So, you can imagine you can blow out quite a bit of pressure at 825,000 pounds per minute, or pounds per hour, sorry, times 7. We've got a tremendous amount of pressure that we can blow out, but that's going to depend on the differential pressure. So when the reactor is at a high pressure and the torus is at a low pressure, it's going to move very, very fast. So we want to reduce the pressure to allow our low pressure systems to kick in. And it's also removing heat, right? If you're taking steam out of the reactor and dumping it into the torus, you're cooling the reactor off. So core spray, our first low pressure system. And again, this one is one of the simpler ones because what it does is spray the core. It is a low pressure system, and if it's a big break, then the core spray is going to kick in and just flood it out, right? 4,700 gallons a minute, and we have 2 pumps, 2 power sources, 2 spargers. So in the reactor, we talked about those spargers that spray the water in. If for some reason one of those spargers falls off, well, I have a backup sparger. Everything is independent on this core spray system. And it can inject a little bit higher, but this is kind of the designed flow, 4,700 gallons per minute. So it starts injecting around 300 pounds. So normally the reactor is above 1,000 pounds, so this wouldn't spray in anything at that time, right? But if we start to lose reactor pressure and because we're losing the water, this can kick in below 300 pounds. And again, at 300 pounds, we're not going to get too much flow, but as it goes down, we'll get higher and higher flows. So it normally gets its water from the suppression pool. So this time we're switched compared to HIPSI, and the backup source is going to be that 100,000 gallon condensate storage tank. So just a big tank sitting outside. So this one is AC powered. So this is, again, a simpler one. It's powered the way you would think. It's plugged into the wall functionally. The logic, the brains of it are actually DC power, but everything else, the motor, the pump, those are AC powered. All the valves are going to be AC powered. And normally the power is going to come from the grid. If the grid goes away for whatever reason, we're going to use the emergency diesel generators. So if one loop backs up, right, we have 2 of these pumps. So we'll use the other loop. If both of these pumps fail, all right, it's time for LPCI, low pressure coolant injection. And that's part of a different system called the residual heat removal system. So this RHR system is used for a lot of different things, but its most important purpose is low pressure coolant injection, because that's for an emergency, right? We're talking about the end times here, and we're talking about our defense in depth to make sure that we cannot melt down this reactor. So we've got 2 loops and 2 pumps per loop. So there's 4 total of these RHR pumps, and they're AC powered again, right? They're plugged into the wall, and that's what's powering the motors. The motors spin the pumps. All the valves pretty much are going to be AC powered, and it has other modes that it can do. It can cool off the suppression pool, and we'll talk about all those modes in more depth and detail when we get around to it. So here is the big picture. So pink is my core spray. I'm taking water from the torus and I'm dumping it up into the reactor, right? So there's one of my paths. Over here on the other side, I got the same thing. I've got another pink loop, taking my water and pushing it in there. So now let's look a little bit more. I've got my RHR system, right? It's taking water from the suppression pools. I can send it through a heat exchanger, but in an emergency, forget about that. I just want to get it into the reactor, and it's going to go through the recirc loops and into the reactor. So, and there again, 2 over here, 2 over here. So now I've lost my AC power. HIPC is gone, or sorry, RHR is gone. Core spray is gone. HIPC is going to take over. It doesn't care about electric power, right? It's got some batteries to power its valves. It's got a turbine here that's coming. The steam is coming from the reactor through the turbine, and that's going to spin this guy and push that water in, and it's going to come in on the feed water lines. So you can see even the way they inject are all independent. So they're all pushing water in through different pipes. So even if the pipe on the way into the reactor falls off, it's not like all the pipes are going to fall off at once. We're still going to have some other ones. And then in orange here, coming off the main steam line, you can see I'm taking the steam from the ADS valves, the automatic depressurization, and I'm pushing it in underneath the torus here. And this green is the out for the HIPC. So here's my turbine, right? I'm taking steam off that main steam line, sending it through my HIPC turbine. And once that steam is used up, we're going to push it in underneath the suppression pool here to let it condense. And then that water, that once it condenses, will actually get pumped back into the HIPC pump, back into the reactor, and it'll start boiling off, and it'll continue to power the HIPC pump until everything becomes stable. Over here's my condensate storage tank, and it's the normal source for HIPC, and it's the backup for core spray. RHR does not have a backup. It gets water from the suppression pool in an emergency. So I tried to talk about this as we went. AC power for LIPC and core spray, and we're getting those from either the grid or from the diesel generators. And it's saying this in more words. So the suppression pool, right? That's our big source of water that's right there in the right next to the dry well. And also it suppresses, if the steam needs somewhere to blow, we can blow the steam in there because it's a very big volume and it's not full of water. It's only about half full. And there you go. It absorbs energy and heat during a LOCA. It's a really good heat sink. And during normal times, we want to know how much water's in there because I might need to throw some steam in. So if it was full, my steam wouldn't go in. And we also want to make sure that it's temperature controlled, because if it's 200 degrees and I start shooting a bunch of steam in there, it's going to boil. And then I'm not going to have my source for LIPC and core spray if I boil the suppression pool. So this one is not part of ECCS. This is another pump that is controlled by a turbine, and it's just one extra pump that kind of backs up HIPC, right? It's not part of this core cooling system, and it's just basically a turbine-powered pump that can put some extra water on the core in an emergency if I need it. So what is a LOCA? You all have answered that one. There are 7 ADS valves. And the preferred way to keep the core cool is just to put core submergence, right? Keep it underneath water. If there's water on top of all that fuel, it is going to be cool. So the normal power supply for core spray is going to be the grid. And then what's the backup for HIPC? If HIPC goes away, I'm going to open those ADS valves, and it's going to depressurize and send the steam to the turbine. So here we go. This is always a test question that people miss a lot. So the automatic initiation signal. So we said this has to work even if the operators all are gone from the control room for whatever reason. They all passed out, they all got knocked out. The terrorists came and took them all hostage, whatever. these systems are going to kick on automatically. So the operators could have kicked them on, but for whatever reason, the operators are incapacitated, so they will kick themselves on. So HPSI has two different initiation signals. So pay attention to these logical operators. You got or, you got and then you got or both. So if HPSI sees a low level 2, so water's starting to drop in the core, and there's low level 1, which will cause a scram, and the water continues to drop to low level 2, it's going to kick on the HPSI, so high pressure coolant injection. So the other signal is high dry well pressure, because if the reactor is leaking, the most likely place for it to be leaking is into the dry well. So if I start to see the high dry well pressure, then I know that the reactor is probably leaking, even if I haven't seen the low level 2 yet. So that is also just automatically going to kick on this HPSI pump. So ADS has a lot more, because when I open ADS, I'm functionally creating a LOCA. So I don't want to do that by accident. So that's a huge issue, right? If I have a LOCA, the last thing I want to do is have 7 more LOCAs in error. So the initiation signals for this one are a lot more complicated. So it has to see all of these at once. It's got to see low level 3. It's got to see low level 1, which you're like, well, if it sees low level 3, it must see low level 1. And that's exactly the case. So it wants to make sure that this low level 3 is not in error. So if it sees low level 3 and low level 1, which that would make sense, right? Because 1 is higher. So we passed low level 1 a long time ago, and now we're at low level 3. So we also have a timer on there. We've got about 90 seconds where we're going to wait. We are not going to open these up until we give the operators 90 seconds to do something before we start automatically depressurizing the reactor. And it also wants to see LIPSI or core spray running. So that's what's going to make up. So when I'm opening these, I'm taking water in the form of steam out of the reactor. I want to make sure that either LIPSI or core spray is going to be putting that water back. So if LIPSI or core spray are not running, I'm just going to have to rely on some natural circulation and some steam cooling until I can get LIPSI or core spray up and running. So it's going to make sure that those pumps are running before it opens up. So ADS to me is by far the hardest one, because you have 4 different signals and they all have to be met. But the reason for that is because we're taking something out of the reactor without putting anything back in. So we want to make sure that that is going to happen. So core spray and core spray and LIPSI low pressure systems are both the same. So if they see low level 3, right, low level 3, they're both going to kick on. So then if they don't see that, but they see both, right, they see high dry well pressure and low reactor pressure, right, high dry well pressure and low reactor pressure. So the reason for that is if we have high reactor pressure, we can't put water in. So it's just not going to work. So high dry well pressure is indicative of a leak. Low reactor pressure tells us that the leak is significant enough that our low pressure systems can kick in and actually start putting water back onto the core. So this is a question on one of the assignments, and hopefully it's something that you understand. Please feel free to come in and ask any questions that you may have about it. So tech specs, that's the law of the land, and we talked a lot about that CFR in this, the Code of Federal Regulations. So they are definitely tech spec required all the time, right? All plant modes. So if we're started up or shut down or anywhere in between, this is still a tech spec system. It's still one of the most important systems in terms of an emergency. So we have the backups to everything. So if I need to work on one of my core spray pumps, well, that's fine, because I have another core spray pump and I also have my LIPSI pumps. So it's okay for it to be inoperable, but not inoperable indefinitely. You have a certain amount of period, maybe 7 days, 14 days, 30 days before I need to get that system back. Otherwise, the NRC is going to come in and tell me to shut down, because we're violating federal regulations at that point. So can the torus be broken? Can we break the torus? Sure. So if we have no water in the torus, it's inoperable. It doesn't work. If the torus is full of water, it doesn't work. If the temperature is 211 degrees in the torus, it's not going to work right, because as soon as I start putting any extra heat in there, that's going to turn into steam and it's going to mess everything up. So I need to make sure that I have enough water in there that I don't start to vortex. So at the bottom of the bathtub, you see that little whirly start to form up. There's our vortex. And we can get that same thing in the torus if we don't have an adequate water level. So we want to make sure that we don't create this vortex and start pulling air into our core spray pumps and our other pumps. An uncovered core is definitely a big problem. So the reason why is because of this. So our rods, not the fuel part, but the metal part is made of zirconium. So zirconium works really, really well in the reactor, but there is a drawback. If we get the core too hot, we start to get the zirc water reaction. So the zircaloy fuel clouding and the steam start to interact, and when they do, they start to produce hydrogen. So the water reaction is going, we start to get zirconium oxide and hydrogen, kind of like a type of corrosion, and that corrosion happens to release hydrogen gas. So there's the reaction in the chemical formula. So once we get above 2200 degrees, you can see it's releasing heat over here. Above 2200 degrees Fahrenheit, it starts to become a self-sustaining reaction. And that heat is going to build up more and more and more and more. And that's going to cause more and more hydrogen. And eventually, we have to do something about that hydrogen. And hydrogen reacts violently with oxygen. So the Hindenburg is a famous disaster where the hydrogen managed to get out and the blimp exploded. So we want to make sure that we keep that hydrogen level low, and an easy way to do that is to keep heat out. So if we're at 500 or 600 degrees in normal temperature, we are not going to make very much hydrogen. But once we get up above 2200 Fahrenheit, we start producing measurable hydrogen, and it's becomes self-sustaining, around 1800 to 2200. And it'll continue to make that hydrogen until basically we've got way too much hydrogen, and we're going to end up eventually with an explosion. So we have to make sure that we can cool the reactor with the geometry. So again, we use that pool within a pool, and the geometry is fixed. It's not something that you have to think about because the original designers made it up and it works correctly. So for long-term cooling, let's say that we have a hurricane, just category 5 come and wipe out everything. We want to make sure that the plant can survive for the longer time. So after the initial emergency, I'm going to switch to my RHR system, residual heat removal, and it's going to start taking heat away from the reactor vessel and dumping it into the torus, or potentially dumping it into the Cape Fear River or the ocean. So we want to make sure that we can cool this thing down for 30 days. So, category 5 comes through, by 30 days, we should be in good enough shape to get back to normal. So if we have a small leak, what system is going to kick on? It's going to be HPSI. If the leak continues to grow, then I'm going to get my lower pressure systems to kick in. So SCRAM and HPSI initiation, if I sense this high dry well pressure, and if HPSI doesn't restore low, then I'm going to have low level 3, and that's going to cause my ADS valves to open and lower that pressure, and it's going to cause LIPSI and core spray to be able to inject. So, as I go down in pressure, you can see some of these systems are going to kick off because HPSI doesn't work very well at these lower pressures because it's using the steam from the reactor to actually spin its turbine. So once the pressure gets low enough, the turbine isn't going to spin anymore and it's not going to be useful. And once we get down to about 20 pounds, LIPSI has given us 10,000 gallons per minute per pump. And remember, there's 4 pumps, so it's pumping a tremendous amount of water. So high dry well pressure occurs. Which systems are going to kick in? We got low level 3, which systems are going to kick in? What's the magic number where we start getting hydrogen? 2200 degrees Fahrenheit. And then adequate core cooling is just having the core submerged. If the core can't be submerged, we can try to cool it with steam, but that's not a pretty place that we want to go to. So there is the halfway point for this video. So please take a break if you need to, and we are going to hop into HPSI. So HPSI again is high pressure coolant injection. There's 2 videos here showing you a turbine driven pump, and you can see how simple they are to get started up and going and everything. So there it is, high pressure coolant injection. It's going to give us sufficient injection to maintain the reactor core covered during a small line break. So a small loca, which doesn't result in the vessel rapidly depressurizing. So we want to make sure we keep it below this magic number, 2200 degrees Fahrenheit. It can automatically initiate, or an operator can turn it on. It doesn't need AC power. It doesn't need the grid. It doesn't need air, and it doesn't need any other ECCS system. And it can give its flow to us within 60 seconds. And there's 3 modes. We got standby, what it's in right now. We got emergency injection, and then we can test it. So here is the system in all of its glory. We have a steam side and a water side. So let's look at the steam side first. It's going to take some steam off the main steam line, come through here, spin this turbine, and it's going to go through some more pipes and end up in the torus, right? So that's the whole steam side. So come off the main steam line, go through the HPSI turbine, come back through and discharge in the suppression pool. So that'll condense the steam and keep that cycle going. So you can see attached to my turbine, I have a shaft, and that shaft is attached to a main pump and a booster pump. So I'm using 2 pumps together because I need to really push the pressure up. So let's look at the water side. It's going to take the water from the torus, which, remember, I just put some steam in here and it condensed. So this is a good cycle. It's going to be self-sustaining because more water is going to be coming in the form of steam condensing. So I'm going to pull the water off here. It's going to come through my booster pump, and that's going to push the pressure up. It's going to come through the main pump and push the pressure up even more, and then it's going to make its way back towards the reactor vessel. So there we go, back towards the reactor. I've lost it. I don't think it's on here. So we've got our turbine cooling system, our turbine lubrication system because it needs oil, right? We have some things on the end of the turbine to make sure that the steam doesn't blow out the sides, called a gland exhauster system. We've got a booster pump and a main pump. So the steam side, we got the main supply, main exhaust, and then some gland exhaust, again, just to keep the steam in the turbine. And we have some drains that are going through there and a couple of vacuum breakers. So here is our simple, main steam line alpha, and we're going to take it off. It's going through a couple of valves. So this one is AC, but we just leave it open. This one is DC, which is controlled by batteries. And again, we're just going to leave it open. So over here is our first closed valve after the drain pot. So any moisture that's in that steam is going to get stuck in this drain pot, and we can just open a valve down here to empty the drain pot out from time to time. So here is our first DC valve, and we just open it up and open up this one, which is hydraulics, right? It's got hydraulically controlled valves controlled by the steam, controlled by oil. So we open this one up. Then this is going to be the stop valve. So basically this one's open or closed. And then this is my throttle. The control valve is my throttle, and I can open and close it as I see fit. So it's going to come through and spin the turbine. And then here is another drain pot just to get any moisture out. And it's going to continue on its way back to the suppression chamber. So here's a pressure transmitter, pressure indicator. And if it sees a high pressure here, it's going to trip the turbine off because it thinks that there's some kind of problem going on. RTGB just means control room, reactor, turbine, gauge, board. So RTGB is just the indicator. They have a gauge in there. If I get too high of pressure in here, these are little diaphragms, and they are going to blow out and cause that steam to go into the room. So if for whatever reason my pressure builds up too high, it's going to blow through a little rubber diaphragm, and it's going to send the steam into the room, which is actually a really big problem. So that's why we want to make sure if this pressure gets too high on the back end here, maybe the suppression chamber is full and there's nowhere for the steam to go, then I'm just going to open it up and dump the steam into the room and hope there's no humans in there. So the steam is coming from the main steam lines, which normally would deliver it to the main turbine, but in this case, it's going to deliver it to the HPSI turbine. So in a standby lineup, it's going to have the steam all the way up to that first closed valve, and the stop and control valves are hydraulically controlled. So the valves are going to open automatically. The stop valve is hydraulic, and if the hydraulics go away, it's just going to close itself because we can't control it anymore if the hydraulics go away. The control valve is the same way. It's hydraulically controlled, and it's also just going to fail closed if the hydraulics go away. So the turbine is what is driving the pumps, and it's a two-stage pump. We saw that before. We've got a booster pump and a main pump. The turbine is called a Terry turbine, and there's a little picture of it, what a Terry turbine looks like, which is not the turbine that you've seen in some other pictures. It does look a little bit different, and the steam just gets caught in these edges and causes this to spin. So where does the steam go to? It goes to the suppression pool, and this is the elevation that it goes in at. We talk a lot about the elevations just to know where these things are. And again, the exhaust, if it for whatever reason can't go into the suppression pool, it's going into the room where the HPSI pump is, which is very bad. So here we go. This OE is basically they didn't perform enough maintenance on the drains, and the water backed up, and the exhaust line ruptured through that ruptured diaphragm, and there were 5 people in the room. So they isolated HPSI, and then they've got people contaminated, and they're taken to the hospital. So it is a very, very bad day to have this ruptured diaphragm go out. So in 2020, when they start this thing up, nobody is down there in the room. You may walk through the room with the turbine on, but you want to minimize your exposure while you're down there. So there's a seal on the ends of the turbine just to make sure the steam can't get into the room. And it just uses a little condenser with low pressure to basically pull the steam. Instead of wanting to go out to the room, it sees a lower pressure over here in this condenser, and it goes that way instead. So now we looked at the steam side. Now let's take a look at the water side. It's got a normal and an alternate path, and it has a test path. We said all these systems have to be testable. It's going to have a minimum flow path. So here we go. This is the one I messed up a minute ago. So the CST is going to come through our booster pump, and it's going to go through here, and it's going to go into our feed water line, and it's going to go into the reactor vessel. So that's our normal water path. Here's our backup path in red, right? So for whatever reason, I don't have my CST available. I'm going to use my backup path, which is just the suppression pool coming into the pump and going back into the feed water lines and into the reactor vessel. So if I drain this thing for whatever reason, or if a tree falls on it, then I have this RHR system to provide a backup. So an interesting thing about this is it just takes a little bit of extra water, and it diverts it to cool its own lube oil and to cause that condenser to form a vacuum. So just, a few gallons a minute are going to run through these two guys just to keep everything cool. And then there's my test line. So if I'm testing it, I'm going to take water from either the CST or the suppression pool through the pump and the booster. And then instead of going to the reactor, which would cause, all kinds of issues, we're just going to take it and dump it back into the suppression pool. And that'll be our path. So the CST water is pretty clean, and going through these pipes might dirty it up. So we don't want to send it back to the CST necessarily. So that can be our minimum flow or our test path. So right there's another opportunity. If I am taking it from the CST, I can dump it straight back into the CST just to make a nice little test path. So instead of going through this valve and into the reactor, I'll just test it by doing this. And then once I stop the pump, I can make sure this valve opens and then closes again, and then I have performed a good test, and I know my system is going to work. Normal suction is the CST, and the backup is the suppression pool. So the suction is going to open up, and if this gets to low, it's going to close, and the torus valves are going to open up. So the torus section opens if it sees a low CST or if it sees a high torus level. And if, for whatever reason, if they think that this is the leak, they'll seal this system off just to make sure that it is not the problem. So the water is going back into the reactor vessel via the feed water line. So instead of poking an extra hole and giving its own injection source, we're just using the feed water lines. So the feed water system that we'll talk about next, which is not emergency related. So in the next test, can be used in an emergency. The test return can go to the CST or to the torus. And we can also have a pressure control mode. So if I just want to control the pressure of the reactor, I can take the steam from the reactor through that turbine and dump it into the suppression pool. And that can help me control reactor pressure. So there's the whole system drawn out. There's my normal path. There's my backup path. The green is my cooling. The purple is my minimum flow. And then the green is my test return line. So if I'm doing the test with CST water, I'm going to dump it back into the CST. So the turbine oil pumps are DC powered, right? Everything on this has to be controlled by batteries, and it does the lubrication. It controls some of the valves. So it's automatically initiations. We talked about this in the last slide. Low level 2 or high dry well pressure. Either one is going to kick it on. So the turbine, if the turbine's going too fast, it's going to automatically turn itself off because it's going to blow itself up if it doesn't. If the water is too high in the reactor, it's going to trip the turbine as well. So that's fine though, right? Because the purpose of this was to fill the reactor back up. So if it sees too much water in the reactor, well, it's done its job and we can just turn the turbine off. The reason why is because we don't want water to get to our turbine because it can cause damage to the turbine. If no water is getting to our pump on the water side, well, there's no point in continuing to run this thing. So we'll turn it off. And high exhaust pressure. So we talked about that. If this builds up too much, it's going to rupture and just dump that steam into the room, which is a big problem. And we can also turn it off ourselves. So all these things are manual. We're talking about all the automatic initiations, but don't forget that the control room can turn these things on by itself. So all the systems are interrelated. We've beat these two to death. So standby gas is where some of the steam and radioactive gases can go. Feed water, it injects through the feed water line. Main steam is where it's getting its steam from. And then there is the larger and more complex drawing that even I messed up a minute ago. So it's very easy for us to forget things. So significant event reports. So they had, some OE is in the middle of that. So OE would be a little one. So S is significant and R is report. So it's a big deal. So some of the valves were binding up and causing issues, and then rupture diaphragms blowing out. So these are things that happened over and over again and caused the system to not work, or caused other issues. So what's the preferred source? The CST, and that is all we have for this week. So please let me know if you have any questions, and I hope you have a good week.